Hi everyone, welcome to the Deep Learning for Natural Language Processing course. On today's agenda, we will mainly focus on artificial neural networks and how we can use them into NLP. Before we get into that, we do have to cover some remainings from the last class. More specifically, we'll talk about how to embed higher structures of words named sentences, paragraphs into one single vector representation. After that, we do start talking about artificial neural networks and some of its main components that's going to be useful for us to understand more, let's say, complex architectures from now on. And then after that, we finish the class talking about name intent recognition, which is an LP downstream task. All right. So far, we have been working to represent single words with one or more meanings into one single vector representation, either through a single vector representation or a multi-sense vector representation. However, this still keeps us in check on representing one single word at a time, and as we know, as we read sentences, paragraph, documents, it would be interesting to have that entire representation in one vector for us. Then, that being said, after embedding those words, one thing that comes to mind is what happens if I embed two words at the same time, or three, or four for that matter. Probably the context that those two words are offering, they would be all placed in one single vector, and then it would be hard to understand exactly which value belongs to each word in this representation that we have. But that's just an example. We're more interested to be able to embed word representations on other structures in text. For example, how we can do this using sentences or paragraphs, or for that matter, why can't we embed an entire document? One of the few things that comes to mind is simply, well, take all the words that we have, average, and there you go, you have a representation for your entire structure. This is definitely a way of doing things, but we'll investigate some other more interesting approaches. So, paragraph vectors, or the paper that named this topic, it's distributed representations of sentences and documents. It was created by the same author from Word2Vec, Thomas Mikolov and Lee, and they come up with a unsupervised algorithm that learns fixed length feature representations from variable length pieces of text, such as sentence, paragraphs, and documents. In other words, we're able to take this entire representation and have one single vector that hopefully will be able to represent our entire document more faithfully than just averaging the words. And also, this goes in the same direction as Word2Vec. We do have a dense vector representation for the words composing this document. And we will say document, but please understand that document can be any structure from text, from a couple of phrases or clauses, sentences, paragraphs, or entirely real documents. Okay? As in Word2Vec, we do have two different implementations. As Word2Vec, we have two different implementations. One is called distributed bag of words of paragraph vectors, and the other one is distributed memory model of paragraph vectors. The first one, DBOL, it's analogous to the skipgram model from Word2Vec, in which one tries to predict the context given a target word. So we have our context, and there is a twist to this, but we'll get there. And from this context, we try to define a specific target word. And the distributed memory model of paragraph vectors, or DM for short, is the other way around. So it's close, similar to the continuous bag of words, in which the context is used to predict a target word. Probably you know paragraph vectors by its nickname. It's called Doc2Vec. It's part of the Jameson API. So Probably you know this already, but just with a different name, okay? In that case, since we have two algorithms, the distributed bag of words and distributed memory, that are analogous to continuous bag of words and also to skipgram, what is new to the table? So on top of the context sliding window that we have, that will represent context and center words now, we also have another vector representation. That vector representation is called the paragraph ID. And this paragraph ID is added to this context sliding window in a hope that as we move this context window visiting different words, this paragraph ID will be able, since it's going to revisit all the text, will be able to capture the semantic value or the representation for this entire document a little bit more faithfully. The paragraph ID, in that sense, it will be shared throughout the entire document for each sliding window, which means that while the words inside this context sliding window will change, the paragraph ID remains the same, simply because on every new iteration, we're going to go there and update the paragraph ID vector. Okay? And if we want to compare the approaches from word to vec with the skipgram model and the continuous bag of word models, what we have is on the skipgram, we use the target word to predict our context. And then on the continuous bag of words, we use the context to predict the targets. Now, on paragraph vectors, we use the paragraph ID to predict our context, and then on distributed memory, our paragraph ID also is used with the context to predict a target. It's important to mention that here, for the sake of simplicity and showing how this diagram works, we put the paragraph ID substituting here WT2, but here, as you can see here, with this context on WT plus 2 is not lost. It's simply to make it easier to show, all right? So for the paragraph vectors, distributed memory, randomly sample consecutive words from that paragraph they are chosen, and then we predict a center word from this randomly sampled words. And of course, we also take the input to this context words and the paragraph ID, meaning that we use the sample words from our paragraph and also the paragraph ID as an input, and we use all of this to produce our target word. And then the word vectors and the paragraph vectors, they are average or concatenated. In the distributed bag of word model, we ignore the context words in the input, but force the model to predict words randomly sampled from the paragraph in the output. So it takes the paragraph ID as the input and tries to predict randomly sampled words from that document. So given the paragraph ID as our context, we use that and then we try to predict words that belong to this document through our paragraph ID. So pretty much you're using the ability of this paragraph ID that's capturing the essence of the entire document to predict certain words, right? We better talk about some of the details on paragraph vectors. S in Word2Vec, it is also a dense vector representation with around 300 dimensions, but as before, you can also set this to 300, 600, 900, 1200 dimensions, whatever granularity you have, and of course, the more dimensions you have, the more granular you're able to capture the meaning of that document because you simply have more parameters, you have more characteristics between quotes to describe your document. On the distributed bag of words, you don't need to keep track of the word vectors since they're not relevant for the prediction. You use them and then you discard. But if you train a Word2Vec model prior to the DBO model, your word vectors might be better represented. Okay. it's also important to mention that before on Word2Vec, word count was actually not really taking into consideration simply because we were looking at one target word and context in that window, regardless of its distance or regardless of its order that you have in this context window. In the paragraph factors, however, the order does play a role because the context will change depending the order that you have. As another detail on this approach, combining the distributed bag of words and the distributed memory does improve results on selected tasks. That was the case at least on document classification, for example. Also, at that time, they actually, in their paper, they show that the distributed memory version of this algorithm consistently perform better when compared to distributed bag of words. Okay, and on the distributed memory, you have also the option to either sum the vectors or average them, but for their specific case, summing those vectors from the words and the paragraph vectors did work better, but that's actually not always the case. It's important to mention that uh, different different setups of experiments, they do require different parameter optimization or parameter adjustments. And I guess it might be worth to mention something here, like when paragraph factors was proposed, right after that, there was this implementation from Jensen, and people were really eager trying to figure out how to replicate the results on their paper. It turns out that things are not that straightforward. Even for the authors working on this paper, at that time, people were asking how to make Doc2Vec perform in the same way that the paragraph factors was reporting, but then as you see here, Thomas Mikolov at that time wrote, I don't know what Doc2Vec is, but you can use my code that I posted here in this thread on October 6th to get around 90% accuracy on the IMDb dataset. That was the dataset they were using in this paper. And if you plan to match Crowley results, you'll have to ask him. I could not achieve the same performance as he reported in the paper. It's just to show that reporting is important, is not as transparent as one might think. Of course, following this discussion, there was other topics, but you can read them. I'll put the link here so you can take a look. And today, at least, if you want to reproduce the original paper, you can definitely use this document from Jim Sim to use Doc2Vec and replicate their actual results. All right. As you can see here, as you can see in this discussion, this far from Google, uh, especially with approaches that do require some sort of hyperparameter optimization, there are a couple of things that people usually do not mention. For example, in word embeddings algorithm, they heavily rely on this hyperparameter adjustments. Some of them, they are really famous, such as window size or number of dimensions, but on the other hand, there's a bunch of other parameters that people usually don't talk. For example, are using what is the minimum count of words that you're using, or what is the learning rate, or how many epochs you're running this, or for your training algorithm, are using negative sample or hierarchical softmax. And there's a bunch of other hyperparameters that usually people purposely or not omit. Of course, sometimes it might slip, and that's fine. But keep that in mind when you're trying to either reproduce or reuse other people's work, right? Some more tricky details that we did not mention in the beginning when talking about paragraph factors. In Word2Vec, the word vectors, they either exist or not. However, in paragraph factors, this relationship is not a direct A to B kind of thing. Why? Because, I mean, on Word2Vec, if you had a word, of course, you train, you get your vectors, and you're good to go. And if you don't have, it'll simply say, well, sorry, the vector's not here, and you get nothing. However, when we are trying to infer a vector representation from a given document that does not belong necessarily to our training corpus, uh, if you just compare the document by its ID, of course, this might of course, will not reflect the test and training set, of course, but as our documents are composed of words, some of those words in those documents, they might appear or not in our training set. And it would be nice to have a way to kind of infer the document vector, even though not all the words exist in our training corpus. Otherwise, to scale the solution would be quite problematic. And because of that, this is one of the tricky details, especially if you're using the doc2vec implementation from Gemsim. Every time you're trying to infer a new vector for a document, you do have to run a small training step to obtain the vectors for that paragraph after the model is already produced. So you have a pre-trained embeddings from documents, so every document has an embedding, and if you bring a new document to try to transform this new document into a vector representation, you do kind of a small training in order to initialize or even to have the vectors for the words from this document, and then you improve this representation through a meaning training step, right? Um, and this is one of the things that people or the literature usually does not spend that much time recording. So it's kind of tricky to know exactly when and how to use those, let's say, iffy ways to obtain the same results. So this was more a thing, I would say, in the past. Like, uh, people usually did not spend that much time in explaining hyperparameters, the corpus, the quality, the data cleaning process, and so on. Nowadays, it is getting better. Is far from perfect, but you still can take a look on some really popular papers, and you will still notice that some of them do not spend that much time on talking about these details. For example, if you take a look on the paper from Universal Sense Encoders from Google, you will see that their algorithm, when they talk about what is the data that they use to train those vectors, you will see things are definitely not that transparent. So try to remember to always have an ethic and also conscious way of reproducing your work with as many rich details as you can, because otherwise it would be really hard to reproduce your work, and also it make it difficult to have a transparent work on this, right? This is not only true from artificial neural networks or, for that sake, NLP, but for pretty much anything you do, especially in machine learning. All right. Just to give you a quick example, this is the small training step that we have from GemSim on Doc2Vec API. We have this infer vector in which you have to provide a document that you want to try to compose the vector representation, and then you have some alpha, which is the initial learning rate that you have. The minimal alpha is how much more you can drop the initial value to here, the number of epochs that you run this training, and so on. There are some other parameters. Just to keep in mind that this is extremely dependent on the task/data set that you have. So you might have a case where a given set of values for this hyperparameter, they work really fine. Don't take this for granted. Run some sort of held out or validation step in for you to understand exactly how is the best way, or what are the best values that you have for this parameter, for inferring your vectors in a better way. All right? Moving forward, we'll now start talking more about neural networks and the different architectures that we can use for different NLP tasks. That being said, I guess the first question is why we want to start talking about neural networks. Well, the thing is, there is really a strong trend in NLP, more specifically on neural language modeling. But before we get into this, probably we should get back and take a look on how the different ages in NLP are divided. So before the 1990s, we had most rule-based systems. Then between the 90s and the 2000s, statistical and machine learning models, they pretty much dominated with handcrafted features and all those classifier models, logistic regression, naive Bayes, random forest, SVMs, and so on. And then starting in the year 2000 around this, we see a shift in the area, not, I guess, not only on NLP, and you see this pattern in many other areas, that some neural language, some neural network models, they start to get some more attention. So in 2003, we had the neural language model provided by Yoshua Bengio. And then 10 years after that, as we saw, we had the word-to-vec model being proposed that starts shifting things around from sparse representation to dense word embeddings. And then in 2017, the attention all you need, which is the basic architecture from Transformers, was proposed, and this got a lot of traction. And I think it's worth mentioning that between the 13 and 2017, we did have some other models being proposed, as we saw, like paragraph vectors or doc2vec. We had glove, fast text, uh, and a bunch of other X to VAC approaches. But then in 2017, we had this attention all you need with transformers. Contemporary to this paper, also we had Elmo, Universal Sentence Encoder, UML8, and a bunch of other really, really interesting contributions in the area. They're all using neural network models. And then 2019, BERT came, and we have this entire area of BERTology, and pretty much BERT still keeps as a strong baseline of many of the tasks still today. Subsequently to that, we have GPT-3 and T5, which is an ultra-aggressive model and a sequence-to-sequence or text-to-text model, respectively. And then now, 2022, more in November, if I remember that correctly, we had ChatGPT being published. The thing is, the story doesn't end there. If we take a look now on the and if we take a look more on the specifics, from 2018 until 2023, we see a lot of models being produced, which is quite astonishing to see how much effort and how much time people are spending on this. I mean, if we take a look on the base of this tree right here, we see the one of the first models, fast text, word to vec, and glove, and from that we have so many things steaming. Like we have pretty much three basic architectures, like encoder only, and these are models most used on classification tasks, in which you transform the text in some sort of encoding and use that encoding to make a decision. And then you have encoder, decoder architectures, such as BART and T5 being the most famous ones per se. And then we have decoder only or ultra-aggressive models more used on the text generation associated tasks. And then here we have the entire GPT family, XLNet and Bloom and so on. Right? One thing that's quite interesting to see here is how the different companies have the most prominent models being open sourced or not. So as we see here, the open source models are the opaque ones. So all of this are all open source, whereas the closed ones are this with a white background. So we do have a lot of models still being closed source, right? Aside from that, if you're looking for some references, and I mean, as we saw, there is a lot of strength. There's a lot of strength in the direction of using neural networks to solve NLP tasks. We do give up on some things, though. For example, explainability is a bit more complicated than if you're using a machine learning model or, for that matter, a rule-based system. But we gain in performance, we gain on scalability, generalizability, robustness, and so on. And that being said, there are a bunch of books that you can take a look about neural networks for natural language and natural language processing. So I'll give this here, leave this here as a matter of reference for us. All right. And before we talk about neural networks, we could, I guess, spend an entire semester talking about the biological inspiration for neural networks, but that's definitely not the goal of this class. The idea is simply to give you a background in which neural networks, they do have their own background on terminology, features, characteristics, and so on, but uh, we can we can pretty much distill this and we can simplify that in a way that if you understand how softmax models they work, then you can easily understand the operation of a neuron, or at least the operation that our artificial neuron will try to mimic. That it's pretty much we're taking a bunch of signals as input. We give those signals some sort of importance. We put this uh, into a special package, in a special formula, and then this will allow us to produce an output that can be correlated with the input. All right, and I guess this next representation makes things a bit more concrete for us, not coming from biology, and I include myself on that. That if you look closely, you see there's a lot of similarities between this mathematical representation, this diagram representation of a neuron, and the biological one. So the main idea in this case here for us is we want to have discrete high dimensionality representation of inputs in a way that by taking a collection of inputs right here and giving them some sort of weighting, and we do this for different inputs, and each and all of them will have a specific weight. We combine this into a weighted sum, and with this weighted sum, we put this into a certain activation function, and then we're gonna have the output, which is nothing more than a combination of all this input that we have. All right. Important things to keep in mind that we want to capture the relationship between input and output in some sort of a nonlinearity, simply because uh, not everything is linearly relatable, of course, and also if we are able to capture this through a nonlinearity, we're able to derive that and wiggle things around in a way that we can correlate the input and the output, hopefully in a better manner. All right. And of course, this here can be composed of can compose multiple layers for our own purpose. So it's not like we just have one node and this will concatenate every single input that we have, but this node here can be multiplied in several different nodes, and we have a concatenation of different layers as well, right? So the first model that we see is the feed-forward neural network model, in which we have one simple activation function f, which acts as our nonlinearity or our nonlinear activation function. So in this, after we do the weighted, pretty much the weighted sum between our weights and our inputs, associating that or summing that with a certain bias, um, we do use that in our activation function in the way that have 1 over 1 plus exponential minus our function, our z right here, that's represented by this function, as you can see. And this will help us to map whatever value that we have z into this distribution, this nice S curve that we see that goes from 0 to 1. So we take whatever final value that we have for z, and then we map that between zeros and 1. And to do that, there are some terms that we should keep in mind. Well, first is our input as x, and then we have our hidden layer, which is pretty much what we fit into our activation function, our bias term that we have right here, and then also our weight with this fellow right here. The W represents how important each of those x's, or how important each of whatever input that we have are for our output. Okay. And the way to think about what is a neuron, think as a neuron can be a binary logistic regression unit, in a way that if for one neuron right here we run one of these functions, one logistic regression, a neural network is the same that running several of those logistic regressions, as in a hope that different nodes they will be able to capture different aspects from our input, and also the importance of this input in our own architecture. And then if we feed a vector of inputs through a bunch of these logistic regression functions, then we get a vector of our outputs, in a way that each of those right here will provide an output for us. And if you have all these outputs right here, we can not concatenate, but we can put them in one single vector. All right. As for right now, there is no need to decide ahead of time what variables this logistic regression are trying to predict. This is actually not important right now. This is just a representation for whatever we want. So in our input layer, we can put words, or we can put word representations or word counts. Well, word counts might not be the best example, but I think you get the idea that this here is not that relevant for us, at least at this moment. So, about classification boundaries, different than a linear regression, a neural network can learn more complex decision boundaries. And this is one of the reasons why we use nonlinearities, or we use our logistic regression to try to find those boundaries in our structure. So if we're trying to separate, let's say, this features here, this data points, through a linear function, we'll see that a couple of them, they do get this correct, but in practice, we'll see that a bunch of them here, they're not properly separated. So we want to move from this linear representation right here to something a bit more flexible, in a way that we can capture the, let's say, the non-linear correlation between, for example, our input and output, right? So, and as we said before, in fact, we can feed this logistic regression into another logistic regression. And then we keep doing this into a hidden layer 1, 2, 3, 4, and so on, until we have enough hidden layers. This is what we call a multi-layer neural network. The thing is, the higher the number of hidden layers you have, probably different of those layers, they will be able to capture different aspects of your data. There is some debate, though, that a high number of hidden layers, at least on NLP, some of them, they can be completely shut down because they don't make any difference. On the other hand, some other work, they do list that if you're working with, let's say, syntax or morphology tasks, early layers, they're better to capture this kind of relationship, whereas later or deeper layers, they're better to capture more semantic aspects. Okay? So, that being said, after going over the feed forward, or the simplest perceptron that we had there, and then our more, in quotes, complicated multi-layer networks, a question that might arise is, yes, are we taking also a look at other architectures? And the answer is kind of. We will revisit some architectures, such as recurrent neural networks, long short-term memory, gate recurrent unit, some autoencoder ones, sequence to sequence, but some of those architectures, they are not actually important for what we're doing. For example, convolutional neural networks, they actually didn't work out that well for NLP, so we'll probably skip a bunch of them. This is more to show to you that don't think that the architectures that we're seeing, the scores, they are the ones that only exist. So there is way more, but we'll focus on quite specific ones. But it doesn't matter which architecture you're using. Behind the scenes, what's happening is pretty much the same thing. you have a certain number of inputs that they will be somehow weighted according to an arbitrary decided weight matrix or weighted vector. And then we take all of this, sum them with some sort of bias. And then all of this, the multiplication between the input and the respective weights that we have, and sum up with some bias, they will be put into some sort of nonlinearity. In this case, here is our function f. And then after we do this, if we were to continue this A1 and A2 nodes right here, these neurons, we would do probably the same thing again. If moving on from this notation that we have here with all the index, if we were to write this into a matrix notation, in fact, we do write that in a matrix notation. And we would say that Z is equal to the weight matrix, the weight matrix times the input plus B, our bias. And this X here represents all the X's that we have. All the W represents all the weights that we have for that specific weight matrix, and X here is for all the input that we have. And then after that, we take that value that we just calculated and put into another nonlinearity in which we'll decide pretty much what's going to happen. This is the same thing here that we do in this other notation. All right. Needless to say, the activation function that we apply into those nodes, like 8.1, 8.1 and 8.2, they happen in a element-wise manner. So it will happen for Z1, which represents X1, W11, Z2, which is 1, 2, X2, and so on and so forth. Okay? And why do we need nonlinearities? We kind of talk about this when we mentioned the boundaries that we wanted to separate. So if we were to have a linear transformation, we would pretty much able to compress all the weights matrices that we have into one single linear transformation. And this is actually not good because we want our weights to be important or to be related according to their inputs in a different manner. We don't want them to kind of be codependent one from another. This would not generalize that well because it's not like always you have that one feature or one input or one attribute is correlated with another. They might be, in fact, most of the times they are pretty much independent in this sense. Well, they do relate to some extent, but not in the way that we would be able to compress them in one single linear transformation here. Also, I mean, the more, let's say, the more data points that we have, we want to be able to approximate this long nonlinearities to whatever real function better describe this data points that we have. And of course, if you match this to some extent, let's say if you match this exactly into one real function, we would have something as this overfitting right here. On the other hand, if you don't approximate that much to the real function from your prediction, you would not generalize that well. You will see that this last case does happen with more modern approaches. They do overfit. It's called overfitting to the actual training that you might have. Okay. But we'll take a look on some of the characteristics of neural networks so we can later explore some of our other models. All right. Another interesting concept that we kind of explained already, but it's probably good to give a recap on this, is about activation functions. It's a really important concept in neural networks that's used pretty much to convert an input signal into an output. Well, not necessarily that. We need, as we are converting the input into the output, we need to make sure that they are correlated somehow. And for that, we need some sort of an activation function to do this for us. We could use just the sum of the nodes, but of course, that would not be that good because by summing up let's say all the nodes, we might not find the best relationship between input and output. Uh, on the other hand, one might say, yeah, what about a linear function such as f of x is equal to ax plus b? Well, you would be able to correlate the input and output, but only this would only be a good correlation if this input and output are linearly separable. So if you have something like this as a linear function being your activation function, such as the one that we just saw, we do correlate the input and output, but this linear model, it wouldn't be that useful, unless, of course, for this example that we are seeing here right now. But in practice, things, they don't happen like this, simply because usually there's no specific linear correlation between your input and output. And if you just have one linear function or a combination of linear functions, which most likely can be described as one single linear function, this would not generalize well, and most likely won't do the decision boundaries. They won't produce decision boundaries that you are looking for. Okay. So, all in all, we want a function that we are able to differentiate, to make the first derivative on our functions, so we can know exactly what is the rate of change of that function. Differentiating a function with respect to a variable, it will help us to identify how the variable affects that function, and this is where we are interested. We are trying to understand in which direction, and with that also how much faster or slower we can change those values in a way to see how this affects our output. And then, all in all, of course, a nonlinear function are those that with which their graph is not aligned. So those examples that we saw before, they are pretty much not that case, right? And then another important aspects is that this nonlinear linear function, as we just described, it has to be differentiable. As we just talk about this, we will get to some more concrete examples on how we can work on with the gradients, the values that we want to change, how we can backprop or optimize this. And I would kindly ask you to remember about backpropagation. We'll talk about this in the upcoming class. And of course, this will help us also calculate the error loss, or the error from our between our prediction and the real value that we have. Okay, so one of the most famous activation function, I think we mentioned this already, is the logistic regression. So the goal of a binary logistic regression is to train a classifier that can make a binary decision about the class of a new input observation. So for any input data that I have, I want to be able to classify this into some sort of a tagger classification, giving a certain confidence value or a certain probability level. And then the sigmoid function or the sigmoid classifier help us to make this decision. So using this classifier, we can classify this new input observation. And within our sigmoid classifier, or our sigmoid function, we do have some interesting features that we should keep in mind. For example, we do have the weight W and then the bias term B. Our weight W, and then we have one for every single input that we have. So every weight I that we have here is a number that it is associated with our feature X, Y on the same index. The role of this weight, for that matter, for this arbitrary weight, at least in the beginning of our training process, it helps us to represent how important a specific input feature is for the classification, negatively or positively speaking. It's not like the weight is just used to give a better, let's say, a better or a high importance for something. It's also used to say that this specific feature is not important for the decision at all. And then later on, when we start doing backpropagation, you see that depending how is your activation function, be that sigmoid or any other function, you see that some of the features that we're using, they're not important for the final decision. And then this weight will help us to kind of regulate this somehow. Okay? Also, the bias term is also called a bias term intercept, and it's yet another real number that is added to the weighted inputs. If we do not have our bias term, what will happen? Pretty much without that, our model will train over the point passing through the origin only. And this is actually not what happens usually. The introduction of bias, it will allow our model, our boundaries to go to cross something other than origin when we have these boundaries, which is quite interesting for us. Okay? And how we combine those weights, inputs, and bias? Well, to make a decision on test or our test instance, the classifier first multiply each and every xy by its weight, and then sums up the weight features, and then add the bias term. So all in all, after we do the dot product between w and x according to their respective indexes and sum up the bias term, we're going to have a z nothing more than a weighted sum for how much likely this specific, let's say, for this evidence for our class. So giving a certain number of inputs and then how important those inputs are. If we do this for all the inputs that we have and add some bias, we'll be able to have this weighted sum that compromises or that results in the evidence of our class, because later we take this value right here and we put into a nonlinearity, or we put this into a function that will transform this value from a scalar to something between 0 and 1. Okay? Yeah, this is just another representation. So instead of writing the entire sum right here, we just use the matrix, or this matrix representation that represents all the indexes and all the elements from W, doing dot product with X, and then we do the bias term. As we were talking before, when we obtain z, that doesn't necessarily translate into a proper probability. What we want is actually something between 0 and 1. So the idea is, well, before we get into this, after we calculate the value of z for all the weights and inputs and bias that we have, we'll find out that this number can be anything between minus infinity and plus infinity, which is kind of hard to advocate giving a certain number if it's just too high or too low, how much that is more or less than the one that you're comparing with. So we need something that to bring this to a more, let's say, a probability range that will allow us to make a proper decision. Let's say the closer this specific value is for 0, most likely is not from a given class, or it is depending how you classify zeros and ones on this. But let's say 0 is let's say a negative class and 1 is a positive class. So the closer you are to 1, or the closer in this case you are to infinity, it will translate in closer to 1, and the closer you are to minus infinity, the closer you would be from 0, right? And yeah, to create this probability from really large values and really low values, we simply pass z through a sigmoid function, and also called a logistic function, and that pretty much what gives the name logistic regression. And how that looks like. So we will be representing our sigmoid function here as y equals to our sigmoid function and z. And if you remember, z is wx, the sum of all the w's and x, wx plus b, our bias term right here. And this here will translate our z value into an actual number between zeros and 1, right? So if we apply the sigmoid function to the sum of the weighted features, we do get a number between 0 and 1, as we said, and we can use this 0 and 1 as a proxy or as a representation for classes. So in the end, we just have to make sure that the case in which we obtain 0 or 1, they do sum up to 1. And in this case, we can see that if we take the formula that we just saw for calculating, transforming z into an actual probability, in this case, if we take 1 to whatever we had it before, this pretty much gives the complement on the other probability. Think as the same thing as when we were talking about distance measures between word vectors, distance and similarity. It's pretty much the same idea here, right? Now we can try to consider the following text and try to make some sense of this theory with actual input values, weights, and biases. So imagine that we have this sentence, and the sentence reads, it's hockey. There are virtually no surprises, and the writing is second rate. So why was it so enjoyable? For one thing, the cast is great. Another nice touch is the music. I was overcome with the urge to get off the couch and start dancing. It sucked me in, and it will do the same to you. So imagine that we're trying to classify this text here as a positive or as a negative. So if we pay attention, we see that some words or some inputs that we already have here identified. So in this here, it doesn't matter what these features are for now. So think as these are handcrafted features or observations, and we see that given that this here represents feature one, input one or feature one, we say that we have the occurrence of 3 times. Whatever x3 is, we have the 1 to represent it. On x4, we have 3, and so on. Now, this is what we meant later on, that these features and these values, they are somehow arbitrary. They don't have a semantic meaning. It's just a representation of what we might use to try to extract some semantic meaning. So let's see, for those features we have the following values. So let's say x1 was the count of a positive lexicon, as we were using here before, like enjoyable, nice, and great. So we have 3 words being part of this lexicon. And then for the negative lexicon, we have 2 words. If the word no belongs to the document, we mark as 1. If it does not appear, we mark as 0. If we have some counts for pronouns, if an exclamation is there, we also mark as 1, if not as 0, and so on and so forth. And the idea is, let's use these features, those characteristics, as an input to our neural network, and hopefully we can come up with some other parameters such as weights and biases that will allow us to make a proper categorization. So for this example, x here, as we saw, are all our inputs. And let's consider that we have some sort of weights here. For those that are already familiar with how to initialize the weights, or later how to wiggle those weights, inputs, and bias, keep that aside. Now we're just doing this forward pass in a way that we're going to use the output to make our final classification in the end. So there, let's say we have this vector W, which represents how important each of those features are for whatever classification that I'm doing right now. And then we have a bias term at 0, -1. If we consider how we calculate the probability that we have for a positive class, in this case, we will say that given the inputs, what is the probability of this to be a positive class? Or if we use the notation that we just saw, what is the probability of y, our prediction here, is equal to 1 given the axis that we have? In order to do this, we consider that we're going to put the dot product between the weights, the importance of our features, the features and the bias term into a nonlinearity, and this here will give the probability of how close, or it will give the evidence for us to infer how close this is actually a positive example. So If you consider, of course, don't forget that the sigmoid function right here is 1 over 1 plus e elevated to minus z in this case right here. Remember that this represents z. And then if we do the dot product between w and x, and then we sum our bias term, we'll see that there is a probability of this set of features giving their importance that this will belong to this specific category, or the category plus, or for that matter, 1. And if we want to see how probable that same set of features and weights would result in something negative, we can just do the 1 minus the value that we just calculated, and then we would obtain this value. Okay? In another example, just to show that this is pretty much independent on the problem that you're solving. Of course, later on we have to find a way to wiggle those values that we have for x, b, w in a way that we can alter this value so we approximate our prediction closer and closer to the actual value that we have for our label. So in this case right here, we have now a different set of values for the input, then different weights, and also different bias. And we want to, okay, what is the probability of our prediction right here? We pretty much do the same thing that we did before. So we do the dot product between x and w. So here 0.5 times 0.2 plus 0.6 times 0.3 and so on. And we do sum all of that with our bias term, and then this will give us a probability for that specific set of features, weights, and biases. For this case, and also for the previous ones that we're talking about, we're talking about using the sigmoid function for that. The truth is, this is, I mean, it comes with no surprise, this is not the only way to represent our nonlinearity, right? But we'll see some examples in about a minute. One thing that we didn't mention here, like in the previous example, we did have the probability of a given label right here, whereas in this example right here, we don't. So you can attribute that given whatever value here, if you reach a certain threshold, it belongs to a class A or a class B, but it's just for the sake of completion. So coming back to our nonlinear functions, the sigmoid function is not the only nonlinearity used out there. In fact, this is not used at all on hidden layers. I mean, that's not true. We do use hidden layers, but not as much as in other functions. Usually, sigmoid and tan-h, tangent hyperbolic, they are used more to give you a distribution, a probability distribution, whereas other functions, they are used more in internal nodes as non-linearities. So a function that's really similar to the sigmoid function, and most of times is always better to correlate input and output, is the tan-h, as we see here. X, given that x is less of a certain value, it will have a flat line right here. In this case, is -1 for y. And if x is greater than 1, it will have a flat line for y and 1 as well. Another way of thinking about maybe I should put this, yes. Another way of thinking about the tan-h is that this is a logistic function rescaled and shifted. We can actually transform this here into this right here, but we won't go over that. Then there's also hard 10. That was the example that I said before. So this here is the tan-h, so the tangent hyperbolic. So we should definitely fix that. The hard 10 is when it's a flat line, linear line, and then a flat line again. This here, we do have some small curve. That's important to mention. Other activation functions that we came across is rectified linear unit, in a way that it takes the max value after the origin. So we're gonna have y equals 0 here for the entire value that we have for x until x is 0. After that, x grows as a linear function. Then, and some of you might already be thinking, well, are nonlinearities those that should be non-linear? Yes, that's true. But you can use this. This can turn out to be useful in piecewise linear functions as well. But let's leave that aside. Another activation function is leaky ReLU, in a way that we take the value of x, and if it's before the origin, we multiply that by a factor of 0, 0, 1, and after that, it's the value of x that we have as our prediction, as our y. And then we have ELU, which is exponential linear unity. You have GELU, and then a bunch of other functions that can also be used in a sense that to incorporate or to correlate the input and the output. We have soft sign, threshold ReLU, ELU, CELU, GELU, and so on and so forth. Given that many options, which one should we use? I guess for building a feed-forward deep neural network, the first thing you should definitely try is a ReLU. It trains quickly and perform well due to the gradient backflow. Uh, However, ConH and sigmoid, they're still used when you're more concerned, or let's say on the later layer, when you're actually trying to draw a probability of the last values. All right? Another important component that we have to talk about when you're talking about neural networks is the actual cost function, or the measure, the distance measure that will tell us how close our prediction is to the real value that we're looking for. So after we're associating or correlating our inputs with our outputs, we need to make sure that whatever final prediction that we have, it does approximate to the real function that it is describing our data. So in the end, all that we're doing, we're trying to produce an estimate for a function uh, of a real function, and most likely we'll never get there, but the closer we get, the better. So uh, and together with this, let's say, cost function, or this error cost function that we have, we want to make sure that to learn the parameters, this case, weight and bias, that make our prediction for each observation training that we have as close as possible to the true value of y, since that in the training we know exactly what is the data that we're trying to approximate right here. And then for doing this, how do we evaluate how close our prediction y prime here, or y hat, is to the y? Uh, Two things are necessary for that. First, we need a metric how close the current label that we have, or the prediction that we have, is to the true gold label. So how close our prediction is the real value. And then an optimization algorithm that allows us to iteratively update the weights so that we can minimize this loss function, or that we can minimize our error as much as possible. And for that, two things are necessary again. The first one, this metric, is a distance, how far things are, prediction, or in this case, current label, prediction label, or evidence, to our true gold label. And the gradient descent, or more specifically stochastic gradient descent, in which it's a mathematical process that we're going to use to be able to randomly, not only randomly change those values, but to actually know in which direction those values for our weights should be changed in a way to minimize our loss function. Um, and as we saw before, before we were just talking about gradient descent, but we do a stochastic in a way that for every sample that we do that, or we do this wiggling around, we don't want our sample data to be in the same order all the time. So we shuffle things around a bit, and this usually makes things better. Okay. Um, then as a cost function, we use the cross entropy loss function. So we use a loss function that prefers the correct class labels of the training data example to be more likely. So we want a function to award that the correct label was corrected guessed in this case. And this is called a conditional maximum likelihood estimation. So we choose the parameters that in this case we're gonna be using from now on. So our weights, biases, there are other parameters that we can also choose, but the idea is to choose the values for these parameters in a hope that we're going to maximize the log probability of the true Y label in the training data, giving a certain set of observations, which is our X input vector here. And then the resulting loss function, it will be the negative log likelihood loss, which is generally called the cross entropy loss. Okay, and how does it look like? We kind of visit this when we were calculating the prediction on our word embeddings when we talk about word2vec, but we'll revisit this. Okay. So assuming a ground truth or a target probability distribution that is 1 at the right class and 0 every elsewhere, and our compound probability is Q, then the cross entropy, or the cross entropy in this case, it will be pretty much the sum of this probability PC times the log of this, let's say, of this computed probability Q here. And because of this one hot encoding, the only term that left in this negative log probability of the true class BC equals 0. But I think we can move this around a bit. So, so for each training example that we have X and Y, our objective in the end is to maximize the probability for the correct class Y. Or, as we saw before, we can minimize the negative log probability of that class. So if I say that I want to maximize the probability of a given label Y given X, is pretty much the same thing as minimizing the negative log of this probability, in which we already learned how to calculate. Okay. Okay. So, some optimization details. You might ask why we simply don't work in maximizing the probability of a given label or a given class. It's some sort of a convention. We do, and optimizers define, they do typically minimize a function instead of maximizing. On top of that, there are some transformations that make things easier to handle. For example, when you log transform this probability into a likelihood function, multiplication becomes a sum. So it's easier to deal with sums than multiplication. You avoid some underflows and overflows with that. It is numerically more stable. It's simply because the magnitude of the likelihood can be really, really small. And if you're multiplying these terms over and over again, you might get yourself in trouble. Also, the log, they will transform small numbers into large negative values in which we actually, actually you won't be using them. Well, you will be using, but they're not contributing to maximize the probability in this case. So, and also by working with large negative values, it helps our machine precision to handle things also a little bit better. So, if we want to calculate the cross entropy loss over the entire data set, we pretty much have to calculate that for each and every single label that we have that, and then in the end we just average them. So before we're just calculating the entire probability or the we're calculating the negative log for that specific distribution, for that specific values that we have and for our label. But then if you want to make sure you have the entire cross entropy on how well this function is approximating for the entire data set, we make sure to sum. Of course, you do this for all the entries and then you just average them. To simplify things, we will be using a different notation, as you can see here. So when we say this fy, oops, let's come back. So when we use fy right here, we're pretty much that we're going to calculate fy with respect to x, which is actually doing the dot product of x with all the weights that we have for that specific input, in this case. And we do this for, let's say, all the dimensions that we have. But we're going to use this matrix notation here because we'll make our life a bit easier. Uh, Another aspect that we want to include right here is regularization. So a full loss function in practice, it has an extra term which we call regularization right here. And this happens over all the parameters data that we have, that we are trying to optimize. And the reason we do this is this will help us to prevent some overfitting when we have a lot of features. This is particularly important when we start to have a large number of features, and you see that some models that have a couple of billion and trillion parameters. In that case, regularization, it has a different of a meaning, but we'll get there. So if we consider now the cross entropy loss function over the entire data set, we have pretty much what we had before, but now we do some a specific term right here, and then we call this regularization L1 or L2. In this case, L2 right here, we are pretty much adding the square magnitude of all the parameters that we had. And if we're doing L1 right now, right here, you would pretty much just add the absolute value of magnitude with respect to the parameters that you're using. All right? But later on, we'll see this in a different perspective. We briefly mentioned this in the previous classes. Also, another concept with our cost function is the gradient descent, which it represents the direction and the speed in which we'll update the weights and our weight matrix. So the gradient of a function of many variables is a vector pointing in the direction the greatest increase in that function. And before, we're actually calculating this for one single variable, but now when we move on to our NLP task, name state recognition, you will see that we have to deal with multiple variables at the same time, and this is actually what happened in most of the cases, but we'll get there. So if we're considering the logistic regression, our loss function is conveniently convex. So we kind of know that we'll get there, when we're trying to minimize our function, our loss function. The thing is, if uh, you change on how fast you change these parameters, you might be able to get there faster. But if the speed in which you're updating these weights is really slow, it might take you a long time to get there. Now, when we are talking about other functions that are not the logistic, that they might not be convex, then things are a bit tricky, simply because if you have a step that's too small, you might be heading your way into a local minimal, and then you are not actually getting to the global minimal. So you might get stuck in this first convex part right here. Then the trick is to find the sweet spot on how fast you want to change the values and maybe wiggle those values a bit faster or a bit slower with smaller or greatest steps. So you can either you can probably overshoot this local minimum and reach out the global minimum for your function. Okay. Later on, we'll revisit that because if you have too much let's say, a larger step, this can also get you in trouble because you can overshoot the minimum completely. But we'll get that later on, right? So, um, as we talked before, the magnitude of the amount to move in a gradient descent is the actual value of our slope. And then this is weighted according to a learning rate, which is the speed or how faster or how slower we should move our elements. In this regard, this alpha right here will tell us how much we should change our, in this case, we're doing the gradient descent here, we are considering W, but later on we'll see that this here can be any part of our neural networks, any parameter that we have there, including the bias term. Okay? Now that we have pretty much all the terminology and the technicalities to minimally understand how a neural network is used to make some predictions, given that we have a sort of inputs, weights, and bias. We can actually apply this to an NLP task, and hopefully we'll be able to motivate enough why this is rather important. And hopefully by this time you already noticed that we're moving away from really meaningful input handcrafted features to something a bit more distance supervised in a way that is not that important what they actually are, but the relationship that those inputs, whatever they represent for our actual classification or whatever task that we're doing. So now let's take a look on named entity recognition. It's probably one of the oldest NLP tasks together with word disambiguation, part of speech tagging, and so on. Okay, so what is the task? It's pretty much defined as find and classify names into text. And what are those names? It can be a location, a person, geolocation, and so on. And the idea is to use this kind of tag for different purposes. For example, we want to track mentions of particularly a particular entity within some documents. Let's say you want to make sure that all the documents, even though they talk about different people, I want to track those people in within different documents. Or for question answering, answers usually are related with entities. For example, who is the person that ate the most cheesecakes in the world? Or who is person X? Or what did Benjamin Franklin did? And so on and so forth. So also, most of times when you're trying to associate factual information, this is often related with name and entities, with people, with person and location. So, what is the largest company in the world? Where is located the country? What is the country with the highest density in the world, and so on. And also, these named entities, they can be indexed, linked off, etc., in a way that if you're able to map what are the entities in your text, you can probably make use of some structured knowledge in lexical databases or even knowledge graphs to try to bring external knowledge that was already created somewhere else into whatever task you have. Okay? Of course, named entity recognition, together with all other tasks that we saw, such as word disambiguation, they are usually followed by other, let's say, pre-tasks. In this case, we can name named entity linking in a way that we relate to different entities, or you'll canonize different entities to one single entry in your knowledge database, and so on. But we can actually take a look at how this looks like in practice. So let's say we have the following text. The decision by the independent MP Andrew Wilkie to withdraw his support from the minority Labour government sounded dramatic, but it should not further threaten its stability in the US. When, after the 2010 election, Wilkie robbed Oakshott, Tony Windsor, and the Greens agreed to support labor. They gave just two guarantees: confidence and supply. Uh, while we read this entire text, we can see already there are some entities that pop up for us. For example, we can see here Andrew Wiki 2010 labor. We see that this wiki here also is categorized in an entity and so on. And we have here the US, which is orange for whatever reason. But think right now we're just finding all the, let's say, all the entities. And then the next step for us is how we can categorize these entities according to some predefined labels that we can later use in other tasks. So we can see that all the persons are all the people here. They're marked as mark all the dates. I'll tag as dates, location, and so on. And this might help us identify or even co-reference different entities within different documents. In order to do this tagging, there is a couple of different encodings for that. Uh, Two of the most famous ones are the bio or beginning, inside, and outside of a text segment for that matter, or the beginning BILOU, which is beginning, the inside and last token of multiple token chunks. But in this case, in any case, all of them they follow the same structure in which you break down your text and then you start classifying them as either a person, in this case PER, O represent that's outside whatever, let's say, entity that you're working with, so it doesn't belong to anything. Then person, mol here is location, and so on. And the BIO encoding, you see that this B here represents every time a new entity occurs. So every time there's a new entity, they will start as B, and the inside of that specific entity will continue with I. And every time you have a new B, it means that you have a new entity going on, right? So what are pretty much the features that we have for name entity recognition? So we have words, the current word that is essentially like a dictionary that we have, and then the previous and the next word that we can use as a context. Um, Other features that you can use are the part of speech, most likely because depending on the part of speech you have, you might be able to identify either a single word or a context word or belonging to a certain entity. And then the label for the context. And this is actually quite important because usually what happens when we're doing this name entity recognition is you want to identify you want to consider an entire context, not just one single word, of course. Just to give you a more concrete example of how this happens, imagine that you have to identify the entity in this news expert right here. Like the First National Bank donates 2 vans to future school of Fort Smith. So if we're trying to categorize this or classify this as an entity, it's not very clear if you're talking about the First National Bank or First National Bank is the actual name of this entity. And this is because, I mean, we're still using a high resource language such as English. Now, imagine transferring this to a low resource in which we actually don't know what is a given entity. So this can be a little bit tricky. Also, in this same news, we don't know if the school is so-called future school or we're talking about a future of a future school that is still about to exist. Needless to say, words that are actually like neologisms or words that are not currently, let's say, traceable or taggable between quotes, they make for a harder case, right? It's not like it's easier if you have a novel entity, you can keep track of them all the time. In this case here, the marshmallow skin is now available in today's Fortnite item shop with a new mallow. So there's a couple of words right here that they're not easily independent, not easy identified. Um, And as we were talking before, in general, classifying single words is rarely done simply because ambiguity and, let's say, more interesting cases, they arise when you try to identify context or identify a specific group of words. In this case right here, and this happens not only in name entity recognition, it does happen in other cases. For example, if you're trying to categorize here Paris, you would categorize this as a location because we're talking about Paris, France, or you would categorize this as Paris Hilton as the person, or again, Paris in Texas, which is another location. And then of course, if you have enough data, if you have enough context, this can be somehow inferred, but still it presents as a more of a complex scenario, right? Um, so, in this case, classifying a word in its context window of neighboring words is pretty much what actually happens in practice. So, the idea for us is to use a specific context, and then hopefully this context, they will act as important features to help us have a certain classification for whatever entity that we're trying to come up with a tag. So it's pretty much similar to the example that we were seeing before, in which, remember, we're trying to categorize a text as being positive and negative, and for that we had a bunch of features, and then considering those features, we would categorize the entire text as class A or class B. Pretty much we can transfer this to named entity recognition in a way that if I have enough context and I'm able to somehow consider the average of this word vectors, and I can give a certain importance to this word vectors, maybe I can use that to categorize a given word in this context. Well, if you were to average those word vectors, of course, and just simply use the average to represent a given text, probably you would lose the information in the position. But if we can concentrate in this context window, and later on we'll see that for this simple neural network classifier, we will consider a specific sequence, things actually work out quite well. So let's say we want to train a softmax classifier to classify a sample word by taking the concatenation of word vectors surrounding it in a window, simply because if we were averaging, as we said before, you might lose some word positioning that might be relevant when you're trying to identify a certain entity. In this case right here, what we can do is, if we're able to come up with this vector representation in which we concatenate the vector for every single words of this, and we say, hey, for this center word right here, considering this surrounding ones, I will take the embeddings, and I'm jumping a little bit ahead on this, but we take the embedding of that word and its context, and we're able to classify this with some degree of confidence. In this case right here, our X or our inputs, instead we were looking for, in the previous example, we were working on handcrafted features. Remember how a positive lexicon appears or a negative lexicon, or the presence or absence of a certain feature. But now we're more interested on the actual running text. So if I have a running text in a specific window, can I use this as a sort of a, let's say, an evidence to categorize if this middle word right here does belong to a certain tag or not. And that tag can be whatever we want. In this case here is we're doing named entity recognition, but we can later on we'll see how to extrapolate this to other NLP tasks. The idea is really similar. Essentially, what we're going to do is we're going to consider the inputs that we have. So we're going to use the same softmax classifier as before. And now we're going to use the input as the word vectors that we had before. And after we use the softmax, we're going to approximate this, or we're going to use the cross entropy error to see how close or how far we are from the actual prediction. And then if we do not get this right, well, we will, of course, in every step update our word vectors. And how we do this, we'll do the derivatives of all those variables that we are considering right now. Before, on word2vec, we pretty much had two words, right? The context and the center. But now, if we look here, we see that we do have weights and biases for, in this case, for this window right here. And this window is composed of different input features that are multiplied by specific weights as we saw here in our softmax classifier, right? This idea was actually proposed and was a method used by Colbert Weston in 2008. Just for the sake of sharing information, this work actually got the ICML 2018 Test of Time Award, and it was pretty much that they used a context window to try to predict what is the proper tag for this center word. So it's really similar to word2vec, in which they visit every single, let's say, word, and sometimes this center word would be the word that we're actually trying to predict a given tag. And if you remember, word2vec was exactly the same thing. We had a running context or context sliding window in which we're trying to either predict the center word, or we're using the center word to predict its context. It's pretty much the same thing, but now we're going to use all the information from our input, and hopefully that will give us a hint what is the proper tag for the word Paris right here. And of course, instead of doing this in comparison with word2vec, in which every single position there we're trying to calculate if that the context with respect to center and the center with respect to context. Now, just some positions, it will actually mean something for us. The other are kind of, as we call, corrupted windows. And how this looks like for us is, given that a window, let's say, not as we saw before, not all museums in Paris are amazing. We would have a true window in a way that the center word does belong to an entity, in this case, location. And all the other examples, so where and when we slide this context window along the text, when Paris is not the same, this case right here is a corrupt window, so is not specifically labeled as a name entity recognition location in our corpus. It might be labeled with something else. In this case right here, it's not. So what is the main idea behind that? First of all, we do have a certain set of inputs in a way that we will use them, these inputs, we're going to multiply them by a given weight. And if you remember, it's exactly the same example that we had before when we were trying to classify the text about hockey as positive or negative. And then we sum this to a certain bias term right here. As we saw, this is the bias term, these are the weights which give us the importance of these features. And then later on, we do put this into a nonlinearity, and then hopefully this will help us also to reduce the dimensionality that we have. So after calculating the dot product of W and X and B, we put this into our nonlinearity. It can be our sigmoid function or any other function that we have. And then we do multiply that by another weight matrix. And then this will give a value for us, a value S, which we can put this S into this value into a logistic regression that will help us find the probability of considering all this context of the center word being or belonging to a particular tag. A couple of things here. We mentioned this already, that U transpose is just another weighting factor that we're going to use later on when we start visiting neural language models and recurrent neural networks. We'll see that, and later on LSTMs and GRUs, we'll see that we use different weights depending on the layer. And this kind of hints already what is the problem with this architecture, although you can get pretty far with this. And then, I mean, we already talked about this. This nonlinearity right here is pretty much 8. It's just associating whatever input that we had here before with the output of that specific layer. And we could have many other layers here, but in this case, it's just a simple neural network, right? So, and we already talked about this, how we actually compute the values in which we want to wiggle our weights and bias and all the parameters. If you remember the word to that class, our cross entropy here with respect to theta represents all the parameters that we want to alter. Before, it was the vectors for the center and the context word and all the other terms with respect to those two words. But here we're talking about a bunch of different biases, a bunch of different weights and bias, and then how we actually compute that. Well, we can do this by hand, and then we backprop all these values throughout the entire neural network, and later we'll see how this actually works. Yes, it's important to remember that this alpha right here simply tells us how fast we want to move our gradient descent here, okay? So, given a function with one output and any inputs, in this case here, all the inputs are pretty much the input value of the words, the vector representation of the word that we have, and our output it will be the final classification, or let's say the evidence that will allow us to do this classification. And then before we just had one word, but since now we have a bunch of them, we're going to have to make sure to calculate the gradient for all these variables that we have now, for all these parameters, including all those words that we have. And this will be the same for the weighting vector, for the biases, for the UT that we had before, the other weighting vector, and so on and so forth. In this case, we can use what we call Jacobian matrix, that given a function with m outputs and n inputs, we can work out that to work out our partial derivatives. And this is actually quite useful for us, but before we get into this, we should also provide some side notes. So let's get into this. So some side notes that will help us to, when we're working with this matrix notation, which parameters we actually have to do the partial derivatives to get a grasp on which values should be wiggled. And before getting into the actual neural network that we just saw, just to keep in mind, if you have this w of x plus b, and you derive that with respect to x, you're going to end up with w, or just the weight that you have. If you do the same w of x of b with respect to b, you obtain the identity matrix. And then if you do, and if you remember, these are all the intermediate steps that we had in our simple neural network in the beginning of this example. So, and if you do the partial derivative of u of t, u transpose with respect to the hidden layer right here, you obtain the transpose of the hidden layer. Now, when we're doing this, the hidden layer with respect to z, actually we have to work out the partial derivatives of all the diagonal terms. In this case, I mean, this will be the final resulting derivative that we have. So for all the terms that we have for the hidden layer here, and of course for z, we have to make sure that we derive every single term inside of this in this case, this multidimensional matrix. I kind of skipped this fast, but the derivative of whatever function that we have with respect to x for all the terms that we have there are simply the partial derivatives for every single unit that we have for those matrices. So if I do a partial derivative of this matrix right here, is nothing more than doing the partial derivative of its inner elements. Okay? And if we do this here, you will find out that every time I equals to j, or in this case the diagonal term, we do the partial derivative of z with respect to I, which is the same as j. And if that's not the case, we're going to just simply mark 0 for all the other cases. And this will give us what we call the diagonal of our function with respect with z here. So let's apply this into our example. So consider our current composition. Let's try to find how to actually wiggle the values from s with respect to b. So our final value that we want to put in our logistic function, how we should wiggle those values. And right now it might sound like a bit theoretical, but in the next lecture we'll see this with some real number examples, and then we'll be able to see how actually changing the values that we have for this case here for the bias, how this will interfere on our final output. But in this case right here, if you remember, this was from bottom up, was the structure that we have on our classification task. So we had the input, which is a vector, we have z, which is the dot product of w and x plus b. We put this into a hidden layer on our nonlinearity. We put this into our nonlinearity for our hidden layer, and then we do the dot product of that. We do the product between u transpose times h in this case. And how does it work? So let's have our side notes here so it can help us out a bit. When we say that we want to actually do the partial derivative of s with respect to b, what happened is by applying the chain rule, we'll see that by doing s with respect to b, first we have to do s with respect to h with respect to z, and then z with respect to b. And these are actually all derivatives that we have if we want to calculate the gradients for s with respect to b. The thing is, we already know some of those derivatives right here. So if I do the partial derivative of s with respect to h is actually ut, so this h term here drops out. Then if we do the 8 of z, we already know that this is just a diagonal function. This is the diagonal derivatives that we have for this matrix. So more specifically is the diagonal of the derivatives of all the terms in which I equals to j. And then if we do this partial derivative of z with respect to b, we obtain our identity matrix, right? And this is, again, we're calculating this for s with respect to b, but we do have to calculate this for all the other parameters that we have, right? So we have b, we have w, and so on. And oh yeah, another way to represent this product between u of t diagonal and, well, here's the identity, we really don't care about this. Another way of doing this here is pretty much doing what we call a Hadamard product, which is nothing more than just the entry-wise product, or pretty much we just calculate the product element-wise between those two matrices. So the first element of this here times the first element of this here, and so on and so forth. Okay. So now, as we were talking before, we do want to calculate now the partial or the gradient of s with respect to w. So we do this partial derivative, and now we have to go and do the same thing we did before. So s with respect to w is s with respect to h with respect to z, and then z with respect to w. But if we look closely, I mean, there's no need to actually repeat the computation of these terms right here, simply because they're exactly the same. So we see that the partial derivatives of this upper, let's say this upper layer right here, this hidden layer in the final output here, they're pretty much the same. So it's actually, we can reuse those calculations because they will be the same for all the other parameters that we have here. So why not to already say that this term here, this delta, is the same thing of doing the diagonal, the Hadamard product between u of t and the partial derivative of all the terms that we have for z. And this, in fact, it represents our error signal. And then we can use this for future calculations and avoid double computation. We'll see that this will reflect directly when we're doing the back propagation. We don't need to recalculate from S to whatever term we want to optimize. We can simply reuse all the calculations done before, and this will save us a bunch of time. Yeah, so this is, I mean, so we can actually, and S with respect to B is the identity. So yes, we see that these terms right here that we have S of H and then H of Z are pretty much our signal right here. So we can apply this for all the other optimization that we might have. Okay. Oh yeah. In this case right here, this is our Z. This is why we simply did not put this value here anymore. So this here, if you remember correctly, is our Z. So if we do the partial derivative of Z with respect to B, we'll see that this is the identity matrix. So the thing is, when we do the partial derivative of Z with respect to W, we'll see that because of the dimension, things get a little bit annoying to deal with. So one way of dealing with that, you'll see very often that we'll change the transpose, or we'll do the transpose of those vectors simply because it will make things easier for us to calculate. So we'll often change the shape as we move forward, but it's just some side note that we have for that. On the next class, we will talk more about how we can actually put this into practice. So right now, we're calculating the partial derivatives for all the parameters that we have in this, let's say, in this composition. But later on, we'll see what actually means that when I'm changing a specific input value, how that changes the overall of my output. Okay. Then here's some reference for today's lecture, and I hope you enjoy, and we'll talk next time, right?